we have Francesco Aprile, and he will tell us about dynamics of the heavy operator.
Thanks, Elvin. Thanks to the organizers for the invitation and for putting up such a nice conference. It's a great pleasure to be back at CIS after many years. So today I'm going to discuss some work based on a recent paper with Daniele Dorigoni and Rudolf Trains, and which is related to other work with Rodolfo Russo, Stefano Giusto, and Joaquin Boas, based again on some work I've been doing in the past that goes back to some older work with James Graham for Reslov and also Pedro Vieira. So the central objects in this talk are going to be heavy operators, and maybe I should say this in advance, a disclaimer. So this talk is supposed to be also a continuation of a talk that Rodolfo gave last week here. So not sure how many of you were here last week, but in any case I'm going to do a 5-minute summary of what Rodolfo said. So don't worry for everybody that came this week, as I came. But nevertheless, let me start with some motivations. So the motivation is that a way we know about characterizing quantum field theory in general, like conformal field theory, is to study correlation function of local operators. And local operators in a CFT, they are indexed by the dimension, spin, and then some quantum numbers with respect to some global symmetries. And of course, in a CFT, two-point function have space-time dependent fixed, three-point function they also have space-time dependent fixed. So the first correlators that are interesting for the point of view of space-time are four-point functions. And among all possible, of course, the simplest are the ones in which I consider four scalars. In this world, there is a particularly interesting categories of class of correlators, which are the ones in which the dimension of these two of the four operators is also heavy. And this is interesting because, of course, you can describe them as a four-point function, but from that point of view, you can also think of them as some two-point function of some light operator, in the case the other two dimensions don't grow, in a background generated by the heavy operator. Of course, I'm saying the same thing, but from this point of view, it's perhaps more intuitive that I can step the problem into first computing the background, and then in the first approximation, try to understand what happens to the light operator in this background. As we will see, this perspective is interesting in the problem I'm going to discuss, and in holography, it also gives some information about the underlying gravitational picture, because the heavy background, if it's heavy enough, is going to generate some new geometry, which is a deformation of ADS. And then when you study the four-point function in particular as a function of the parameters, for example, of the heavy states, that is going to give you dynamical information on the gravity side. And this is what I will try to discuss today. I won't be super general, not any holographic theory is the one I will discuss. I will discuss in particular a class of operators in unequal force superior means, because I want to be super precise, both with the duality and with the physical picture that comes with it. I believe many statements will be general, but for this talk I will focus on n equal 4. Now, a class of operators that are among the most fundamental in CFT are those related to the stress tensor. So in n equal 4 superior means, there is a sector, so the stress tensor comes into an n equal 4 multiplet, and the conformal primary in that multiplet is a scalar field of dimension 2. Now, this might have a representation in free fields. Let me say it as trace phi I, phi j, so it's transformed non-trivially under guard symmetry, symmetric tracer representation, or also said with 20 prime. Out of this field, then I can construct some multi-particle operators of this fashion, where P is essentially the charge of the multiparticle. And I can construct also another operator that will be important later on, which is some exponential series in this O2. Now, for reference, I'm going to call this later coherent state operator. And I'm going to call this maximal trace. Okay. Now, let us start then following the logic I explained before from the edit background. The idea here is going to be that at the end of the day, I'm going to take one of the parameters of this heavy operator to be as heavy as the central charge. Okay? And if this is the case, then it must happen that the heavy operator, as I said before, deforms the geometry. And the first task is going to be to understand what is the geometry in this special sector of the stress energy tensor. Now, this is a special sector because, in general, as you know, string theory comes with 10 dimensions. But for this particular class of operators, I can restrict myself into some consistent truncation of the full 10-dimensional space. It's a famous consistent truncation worked out by Pope many years ago. And therefore, in this consistent truncation, I'm going to simply ask a very kinematical question, because here I'm just interested in some half-DPS state. So essentially, all my state is going to be fixed by symmetries. And therefore, if I ask what's this half-DPS state in this n=8 consistent truncation, the answer is just one, which is sometimes called radius bubble, which should be some metric and which contains, now we'll describe some fields, and this is the part that it overlaps with the talk with Rodolfo. So I'm going to summarize it a little bit quickly. Let me draw some pictures instead of writing the metric, the gauge field, and the scalar fields, because the pictures are more useful. So initially, this geometry is found in global ABS, which we can picture as a visual cylinder. Of course, it's not just, it has some fields turned on. So the fields that are turned on is the metric, then there is a gauge field, and then there is a neutral scalar field and a charged scalar field. Okay, so this deforms the geometry in the bulk. So in the bulk, in the center, the geometry is not ADS, it's actually Minkowskian. This doesn't look like a two-point function, but we can make it so to make more contact with the idea of studying first the wave background and then the fluctuation on top of it. So this is simply done by some conformal transformation, where you take this radius and the time as follows. Which essentially means that I'm going to draw this picture like this. So this geodesic in the middle is going to stay the same. Here I will have my heavy operator inserted, which I'm going to call H. And then somehow the foliation in cones in cylinders here is a foliation in cones, and I can think of a foliation in radial quantization in the boundary. Okay? So this is Z, and then this radial coordinate here is just some space coordinate here in my Euclidean boundary. So now I have an operator inserted at 0 and an operator inserted at infinity. And how do I characterize the geometry? Well, this geometry now is characterized by three-point function, which means I'm going to insert somewhere here and here the dual of the fields that I'm considering. And in particular, this geometry has some expectation value for the stress energy tensor, which for n reference I'm going to write. There's a parameter Q, which is the only new parameter in the geometry. Then there is some expectation value for the current, there is some expectation value for the neutral field, and some expectation value for the charged field. So in this setup, since I have Aprile supersymmetry, I can put all of this together, and actually the only new information is about this guy here, which is going to take this form. So now I found the geometry and I need to solve the inverse problem, which is, okay, what is the operator that generates this geometry? It must be, since I'm a consistent truncation, it must be writable in terms of this class of operators here. And something that is going to come up later on is the fact that it cannot just simply be dual to an operator like this, maximal trace, for various reasons. One is that this parameter Q is continuous, while this parameter P here is quantized. Second reason is that if you look at the 3-point function that this guy can generate when there are two of them equal, you are not going to find the expectation value like this. No, you're just going to find the expectation value like this. So in particular, this means that it's not a negative state of dilatation operator, but more generally will come written as a sum. Okay? So we'll consider a sum over all multiparticles, summing over the multiparticle length. Now, the inverse, so you make this sum, and then you ask, okay, how do I fix the coefficient in such a way that I'm going to match my 3-point functions? 3-point functions of RPPS operators are protected, so I can compute them in free theory, and that's why I solve the inverse problem. And the surprise.
Can I ask a little clarification?
Yeah.
The scalar phi and then the eta e to the I theta, in which so phi is in the multiplet of the stress energy tensor. Is this correct or not?
All of this is the n=4 multiplet, but here I'm preserving.
Good. So you break the 20 prime into a way that some of it becomes little phi, and
Yes,
the
some
other
of-
eta.
Yeah, correct. So some of this in the n=2 formulation of this consistent truncation, this is outside. So when I solve the inverse problem in the way I said before, surprise, the design operator is going to be exactly this operator here with the parameter alpha, which is related to the parameter Q of the geometry in a precise manner, which is the following. Okay. So this is the relation between that alpha there for the operator and the Q parameter in the geometry. Now, of course, as I'm discussing this problem, I already solved part of it because I already have 3-point function here. So the next step is to compute now some light probe in this background. And, okay, so yeah, one more observation which comes with your question. So somehow here I'm arranged the things in such a way that the operator O, or the fundamentals here, field in this game is not the most general one, but it's going to be just trace of x, where x, y, z are going to be the three scalars, three complex scalars. Therefore, what is this expectation?
O squared, yeah.
Thanks. X squared. So what is this expectation value here compared to this one? Well, if you try to arrange a diagram in the free theory, you will see that phi essentially is a diagram where you have some x, 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 x for the multiparticle, x, 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 and then you have x, x bar because it's neutral. So this is going to be some configuration like this. And instead, the one that comes with eta has to come from some sum of diagram which are of the form like this, where you have x, 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 x bar, x bar, x bar, and then you have x squared, okay? Because that's charged, and therefore you're gonna do some contraction like this, some contraction like this. So this guy is actually a two-point function. In disguise, okay? So now you can also ask yourself, what's about this specific combination here, how does it come up in the free theory? Well, you need to compute the norm of this state, okay? And the norm of this state is gonna be some non-trivial function of alpha, and after you have done so, you will see that the norm of this state is actually given by something like 1 minus 2 alpha squared, and squared minus 1 over. Okay? So the norm of the state is always well defined as long as alpha is in the interval 0, 1 over square root. Alpha that goes to 0 means also q that goes to 0, and if q goes to 0, this three-point function goes to 0, which means we are back to ADS.
The fact that this is not an eigenstate of the dilatation, what does it mean for the geometry?
No, that's the geometry. The geometry is not an eigenstate of dilatation. It cannot be so because if you try to construct the three-point function of two of these guys, say this is my h tilde, okay? H tilde can only have some three-point coupling like this, which is the neutral one.
In the cylinder picture, is it time dependent?
Is spinning on the sphere, but it's time independent in this.
And what happens at 1 over root 2?
A good question.
Is it trapped forever?
We will have to take some limits,
Okay.
and we haven't explored that.
But if you increase alpha enough, you might expect you form like a trapped surface and you get a black hole instead of that.
Well, the expectation is that the other way of thinking about this is like to think that we come up later on is that this guy are not totally unrelated, because I'm in some large n limit, and therefore you might think that in some parameter space this operator here is picked on this particular contribution is sum, and then when the norm of course goes to infinity, this is a peak that is not anymore a peak, and so something might be interesting there, but the precise state. Okay, good. So the geometry is a coherent state, is not, and it's what it is.
So for the question of the dilatation, so we are in a background where we have broken conformal symmetry. Is it some more advanced version of Coulomb branch or Higgs branch, but maybe more because you make this
I mean,
explanation?
I really, what do you mean by broken conformal symmetry?
Because
These are the all three-point function compatible with conformal symmetry. Is a stick conformal symmetry.
but if you give a verb to an operator,
Yes.
you somehow break conformal symmetry. Like clearly your theory before had it, but you introduce new scales by doing so.
I mean, the CFT is going to be, there's going to be a CFT with conformal symmetry. And this is just the background.
Yes, sure, but now
Which is
you
alpha
go,
dependent.
you go to a new background,
Yes.
which the background breaks conformal symmetry.
No, but the background, the background, yes, breaks some isometry with the spot. That's what you mean.
Yes,
Okay, good.
all conformal symmetry, like scaling. for
I mean,
example.
let's not confuse. And the boundary is always conformal symmetry.
I see. So the point is that at infinity this goes away, but as we go in.
Yes.
But
Okay, so it's not some type of.
there is
long-
conformal symmetry, but not when you are in the heavy state, right? There is conformal symmetry.
You will see everything is consistent with conformal symmetry, and actually a two-point function will be a four-point function with
Okay.
full-fledged conformal
I
symmetry.
mean, the point is that if you give a verb to an operator,
Yes.
you automatically are introducing a scale. So this
Yeah, it's gonna be
automatically
alpha, yeah.
breaks conformal symmetry. The scaling. So if you act.
I mean, there is a parameter in the operator, but everything has conformal symmetry. Just your four-point function depends on more parameters. The operator depend on parameters in general. So
But I mean, what I think she's trying to say is that if I compute the verb of t in a state, if the state is conformal invariant, the verb has to be 0.
Yeah, exactly.
Yes.
So the state must not be invariant under
I mean,
conformal
this is a
symmetry.
three-point function. I'm not
Yes,
Yeah,
yes,
yeah.
yes.
So this
Three-point
as
function
a
are not
verb,
conformal, is that the state?
No, that's perfect. I think if you, I mean, this one function in the stated is not like t is not conformal in theory in the state, but I think this is what Alice is saying.
I'm not sure that I understand the notation, but
No, I
it's a
think
three-point
it's
function, it satisfies all the axioms of three-point function.
That's,
no,
that's
that's
perfectly right.
Some isometry is certainly broken.
Yes.
Good. More questions? Now I'm going to compute so here I am in the first thing I can compute, of course, is some excitation of this O2 light operator in this background. So I can compute O2. And you have background, which means in the picture I'm going to put some O2, say, at point 1, and then some O2 at point XX bar. And now in the geometry, the way to solve this is to solve the box phi equation, five-dimensional on the dilaton equals 0, and then use some word identity. To relate the actual operator that is equal to the dilaton to this O2. Okay, when you've done this, then you are going to find a formula that I would like to keep for some time. So let me write it. Well, I'll be like this. Now the box phi in this background, as Pink Rodolfo explained in some more detail, but for this talk, you will just trust me. Becomes some N equation, or an equation, and the connection problem that is going to give you the two-point function in the background has been solved in a very nice paper by Giulio Cristoforo, Nelly, Anzini, someone else. Right? So in particular, in that some notation is an equation depends on the following parameter. There is singularity at 0, at 1, at infinity. Then there is some movable singularity at t with this parameter, and finally there is u. Now t here is going to be minus 2 alpha squared over 1 minus 2 alpha squared. Then h0 is going to be n plus 1 squared. At is going to be 1. It's going to be infinity. A1 is going to be 1 quarter. 1 over square minus square, and u is going to be 1 quarter square minus square plus other stuff. So very concrete formula. And at the end of the day, you write this two-point function as follows. So you have n squared for 1 over g5 of Newton, and then you have the following form: sum over r equals to 0 to infinity. There is some object which is going to be important. And I'm going to do some rest integration to pi. Now, how does this factor here, which is important, look like? Well, you can write it as follows, since it's going to have a physical interpretation, and as a sum over some additional variable kappa. And then you have Now this A is the period of a cyber-Witten curve, which you can find through the Matone relation. Let me just not write that. But importantly here you see that here this A is going to give you some pole for the summation when you integrate in omega. Okay? So it means that it's going to give you at the end of the day some mass for some exchanged operators. Now what are the exchanged operators? So here if you you can think about these and these as some heavy light limit of a conformal block. Okay? And in this heavy light limit I'm going to take the light O2 close to the heavy O2. And the poles that I'm going to get, they're originated by this period and are the bound state of the, essentially the masses of the heavy light bound state. Okay? This is a rearrangement of the original formula, and the original formula actually comes from some set of gamma functions, which have this form. Where the epsilon parameter in the end of the day is going to be some minus integer, so one of the way to get to this is to take some particular limit. I mentioned this for a question that I will leave there as I go on. Now, what can you do with this formula? First of all, do you believe it? This has never been computed before, so what can you say about this? The idea is that you can say many things about this independently from the CFT. And the reason is that you might think that the limit in which alpha goes to 0 is a limit in which from the heavy state I recover the series expansion of the exponentials, so I recover identity, O2, O2 square, etc. And therefore in the CFT you can study the small alpha expansion of this correlation function and then make some predictions. And out of the prediction then check whether they agree with the result that you get from here. First of all, it's not at all clear that the limit alpha goes to 0 should be valid, since this is a formula that is originally computed when I am in the heavy background. So if it works, this is again an additional check that everything is consistent. In fact, you can do this. So, but I will not. I will just write here schematically.
So can I rephrase
Yeah.
what you said? So the fact that it holds, does this mean that it doesn't renormalize as you change the coupling?
No. This is a correlator compute a strong coupling. I'm gonna see in the second part of the talk. I compute the exact integrated correlator exactly in n, strong, and lambda, or
Yes.
tau, and gonna be different values depending on strong coupling, weak coupling. So this is like a super complicated object, which here I'm just looking at 3 levels. Okay. Now maybe it's good because I can explain some more what I mean by 3 level. So schematically, what do I have here? I have some heavy operator inserted, and then I have some light operator, and I'm thinking that I want to write this as some, okay, when it's the identity, it's going to be just a 2-point function. Then there is one insertion of 2, and then I have this. Then when I have 2 insertion of 2, I'm going to have something like this. So let me count the vertices. Say that I have 3 insertions, I'm going to have this. So if you count the vertices with the 1 over n expansion, then you see that this is a standard 3 level, 1 over n squared, because each vertex counts with 1 over n. But this is 1 over n to the 4. So this actually goes together with another contribution, which is a loop contribution, which is as follows, but is disconnected. Okay, so you can always, this 3 level here doesn't really mean just 3 level from the point of view correlator with fixed charge, but it means that is the contribution that survives when you think of these two on two fictitious points. So this is a 6-point function, and then you're going to take the limit when the 2 and 2 goes together. So it's tree level in that sense. Good. So, so the prediction that I can make from the CFT have to do with the superconformal symmetry first. Since remember that the O2P operator I actually start with is in 0 to 0, so it's non-trivial representation. So the actual 4-point function, of which this is just a slice, has more structure, which I'm not going to write, but has more structure. It must be consistent with whatever result I get. And this match, in particular the word identity, for example. Then from the CFT you can predict contributions for the semi-short operator exchanged, and also for the long operator exchanged, some of them, not all of them. And by this it means that I'm going to produce for you not just a number to match this, but just some function of one variable, and here I have 2. So one variable slices of this need to be matched against whatever I predict from the CFT, and this also is quite non-trivial and matches. Finally, I'm going to match with something that brings me to the second part of the talk, which has to do with what is nowadays called the integrated correlator. Of course, in the limit when m is large and lambda goes to infinity, which is a formula of the following form: integral dr d theta, some r cubed sine squared theta, and here essentially there is this that formula over there. I'm going to be able to predict this exactly, okay? And then from the prediction in the limit, I should match the integration of this guy here. Now, let me anticipate some questions. Is that if I restrict this integration to tree level, therefore I really use D, this should give a simple result, which is 1 minus log 2 squared, 2 alpha squared. Now, it's not simple to understand how this simple result comes out from here, essentially because the way we are trading this is to use some series expansion in alpha, but there should be some connection with the Sever-Witten curve, etc., that somehow trivialize this statement for this particular function and the particular A that I'm considering. So I don't know this statement. If somebody knows more about the Sever-Witten stuff, please let me know afterwards. Perhaps the formula with these 3 gammas should make more sense when you do the integration, since of course when you split this into sum over bound state, you still have to deal with another sum. Okay, so this was a spoiler. Question? No. So now let me go a little bit more into what it means, this integrated correlator, which here I just anticipated. So first of all, what are you integrating and why? Should be the first questions. There is a story which goes back to a very beautiful paper by Binder, Chester, Pofu, and Wang, where they realized essentially that there is a relation between a particular integration of 4-point functions in an equal form of RPPS operators and some object that you can compute from the partition function of n equal to star on the S4. Okay? I'm not going to explain this connection, it's kind of well known. Well, not well known, but it's well established. This means that regardless of whether you know or not the correlator, you can use the Pestum localization to compute the partition function on S4, and after you've done that, with some extra manipulation, you can obtain a prediction for the in particular integrated correlator that it corresponds to. So, said in these words, the particular measure that the integrator I need to use to integrate the correlator comes from supersymmetry. But you can also think about it in more simple terms, in the sense that it's the unique measure that you can consider in a 4-point function where you have conformal symmetry, which is simply the x1, the x2, the x3, the x4 over the volume of S2, 4 times some function h, which by the superconformal word identity is closely related to the one just erased. Okay. Now this h here, in the way I've set up the problem, is exactly the well. When you do this, when you set up the problem, then you get back to this equation here, and therefore this is the particular measure that arises just from the conformal group diffusion. Of course, there are other kind of measure, and actually there are more integrated correlators, but for this purpose, for this talk, this is the simplest we can use, and this is the one I'm going to discuss. Now, it's non-trivial to manipulate the it's a non-trivial operation to go from the expression for the integrated correlator to the expression of the integrated correlator with respect to the localization to the partition function S4. First of all, you're in S4, here we're in R, on R4, so there has to be some non-trivial operations. And it turned out that the best way, so after the dust is settled, it turned out that the best way to represent the integrated correlator, which I'm going to denote with calligraphic C, okay, which depend on n and tau in the complexified cardinal mills, is to use some modular invariant decomposition. Of course, in n equal 4, any observable must be modular invariant, and so it is going to be the case also here. The point is that there is a well-established literature to do that, which simply says that any observable then is going to be writable in the following form. When here I have some modular functions which are sometimes called real analytic Eisenstein series. Okay. This is not the full spectral decomposition, if you're wondering, but is the one that is used here. The full, so this is in particular the spectrum of the Laplacian or the continuous one, and this is just correspond to the eigenfunction, which is 1. Okay. Now there are some interesting property of this modular function, and also the integration with respect to contour that is going to be showing up in the next formulae. So let me just tell you what they are. So in particular, here you have always a relation of the following. And since the contour is invariant under this relation, then all formulae are going to be inherit this dependency S and times 1 minus S, which is the right value.
Sorry, can I ask you maybe so
Yeah.
that you wrote the formula with the log, but that was really for H as the coherent state.
This is the formula for H, the coherent state. Yes, I'm going to come to that.
Okay.
This is true always.
Yes.
Now I'm going to specify it in such a way that I can compute them. Okay? This is a fruitful exercise because you will see that we need to pass through the operators, which I denoted before as maximal trace, because I'm literally going to build the exponential operator out of this, and therefore make a formula for the integrated correlator.
Are you going to do it passing through the sphere, or it's not in
The step of passing through the field, I'm going to skip it, and I'm going to give you the spectral parameter here, because that's the simplest formula.
Okay.
When the dust all settle, from what you have to do on the partition function S4 to the operator, these are going to be nice. That's the point.
So there is a way to do the mixing for the exponential, because you have to do
Yes,
this.
yes.
So there is a way to do it directly for the exponential.
No, that's a good question. So I'm going to build it from scratch, essentially, and then we're going to discover that for the exponential there is some nice feature, but I don't know exactly how to relate it. It's going to be an open question for the conclusion.
But the way you use localization is
Yes.
with these guys, the O2 to the P over 2.
Yes, yes.
Yes, so that's the point.
Yes, I'm going to build my formula for the heavy state that corresponds to geometry out of these guys, and we're going to see what happens. Okay, so as I was saying, with the data set, the only important things here are these spectral parameters, and I'm going to first build my operator, expansion operator, constructing integrated correlator for them, and then putting them together. So now here I'm going to add the P, okay, which refers to the integrated correlator where I have essentially OP, and then O2. Now, the spectral parameters for this guy are relatively simple. And they take a form which is CPN, is going to be actually the product of some n, which also depends on s and n, then some other slightly more complicated factor, which depends on p and n and s. Okay. Now there are. Let me just write what is mn, just to show you the formula. Mn is going to be some n squared. Well, actually, it's going to be always some invariant combination under the spectral duality I mentioned before. And then this is essentially some polynomial for fixed values of n, is some polynomial, which I'm writing in this fancy way, but that's for fixed value of n is some polynomial. You see 2 minus n, so when n, for example, is 10, this is some polynomial. Here, this FP, and it's going to have some similar formula, but now there is dependence on both n and charge p. So it's going to be a formula like this. S1 minus S, 1 minus F2. Again, I'm going to write some fancy formula, but just for finite values of n and p. This is again some polynomial, and I think I forgot here some pi over psi. So in general, this CP is going to have poles because of this factor, but then multiplied by polynomials. However, this is not the situation I'm going to be in, because I want to take some large n limit, okay? And then I'm summing over all of them, so I would like to have control also on the case in which P is large. Okay? Just to be sure that nothing goes wrong when I sum all of them from 2 to infinity. So I will first study the case in which of the maximal trace operator, and then I will beat my series. It's non-trivial to obtain the expansion in large n and large p in this case, because, for example, you can see here that you have a competition between this lot of the 3f2 and this other slot of the 3f2, so one needs to be a bit careful. The simplest case is the one of mn, but since I'm running a bit late, let me skip it. The idea is that you actually construct some generating function for a parameter, and then you use Cauchy integral to get you use the Cauchy integral as a projection to get the large n behavior. And similarly, one does this for this P. Okay? So are there any questions before I start this? Just maybe up a second. So the procedure I told you before to compute the generating function and then use some trick with the Cauchy integral produce for you some genus expansion of both this factor m and this factor, which for sake of completeness I'm gonna write some of them. So this will be something like g from 0 to infinity, and it's going to be m minus 2g, and there's going to be some m minus s, and then the genus g contribution, which is a function of s, plus the one which will change s to 1 minus s. Okay. Let me just write this m0, for example. We're going to find some formula like s minus 1 half, gamma of s minus 1 half, gamma of s minus 2, gamma of s plus 1, tan pi of s. Okay? And doing the same procedure for the f, but in the case p. Okay, so we're just going to deal with p. You find a similar genus expansion. F, Pn, S is going to be some 2 minus G, and then there is going to be some F of G of S, infinity. And now, because of this competition, when I do that procedure there, I need to decide how P to see how this ratio P over n squared scales. Okay? Depending on the scales, I'm going to get some different F. Now, there are 3 cases. So this may scale like a gamma into 0 and 2, gamma equal to 2, and then actually there is some gamma into 2 and 3, and then gamma bigger than 3. Each one of these cases can be studied. For this talk I'm going to be interested in this, since in that case I'm going to have P over n squared fixed, and which is a quantity I'm going to call Q over 2. Okay? Where Q is actually the same parameter. We'll see that is the same parameter that is in the problem. So an example in the case for the F0 is again some sort of hypergeometric S1 minus S. There is some 1 and then there is some minus Q S1 minus S. Okay?
Maybe it's a bit of a technical, but is it easy to see why this gamma, why these 3 matters from the field 2 that you have there? Like why do you have that transition of gamma equal 3?
Yeah, so when you, it's not a formula that I'm going to display, but when you do this trick that I mentioned before, writing the generating function for P, okay, then you're going to find a formula in which in a certain point there is some gamma minus 3.
But it's not easy to see it from the field.
No, it's not at all easy. Yeah. So from here you can just infer that the limits are going to be kind of tricky because of competition between these and these. But how is not? Good. Let me keep this here. now that I built there's a feature of now that I built some expansion for M and F, then I can put them together and write some other expansion for the spectral parameter. Okay, and of course this is going to be just since this is the product, you're going to get some product of these expansions. What I want to point out about this is that, so I will have again some sum of g 0 to infinity. And then it's going to be some n minus s, some a of g, which is like a0, f0. Or if I go to genus 1, it's going to be the sum of the two. Okay? Is that in general, the spectral parameter is going to be something that is factorially divergent. This means that when I compute the integrated correlator, this calligraphic P of n, I'm going to find, first of all, a term that is coupling independent, which is as follows, n squared over 4, and this psi q plus n squared minus 1 over 2. And then the genus expansion here is going to be given by some n2 minus 2g, g that goes from 1 to infinity now. And here there are some functions where I sum over okay, where these bk here are factorially divergent. So even though the observable is well defined, now this representation is factorially divergent, so I need to fix it. Fixing this goes into some piece of mathematical literature, which was developed by Daniele Dorigoni, which has to do with modular resurgence. But before going into that, let's see what we can say, at least from the perturbative part, regarding the heavy light operator that I was interested in. Now, when you consider the heavy light operator, then I'm going to do some calligraphic C for the integrated correlator. Now, this is literally built by expanding e to the alpha 2, okay? And when you do that, you notice the following. So this is going to be then now, there's going to be some C, which is an L, plus the integral, the spectral parameter, nice and serious. Now, this in the end of the day is going to be some function which is of the form f of n s, because this does not depend on the charge, and then some sum over the charge p from 2 to infinity of some factor that comes from the expansion series of e to the alpha 2, and then the previous f term for the maximal trace operator. Now this sum that looks actually complicated, and because you might say that okay, this f is complicated, right? For example, here you see that not even the tau independent term has factorized form into the charge dependence and then dependence. Magically becomes some m of n s times 1 minus some 2f1 of some parameters, and then 2 alpha squared over 1 minus 2 alpha squared. Okay, and none of these parameters depends on n. So this sum here somehow unmixed the independence between p and n, and as a result, the spectral parameter for the heavy light operator is the most simpler ever. It's actually super close to the integrated correlator when you just have 4 O2s. So this is the simplest example. In particular, this means that if I want to know the genus 0 contribution, if you look here, it's going to have the same structure as the one for the maximal trace operator, but because of the genus 0 is factorized. And then there's going to be a big divergence of things between the genus expansion of the maximal trace operator and the one of the heavy like correlator there.
We have
Yeah.
5 more minutes, maybe
Yes.
you can start wrapping it up.
I'm almost done. So, and something nice that you also notice is that in this genus 0 correction, the parameter Q appear, but if you look back at the formula, from this equality between the spectral parameters at genus 0, you find again the relation that I pointed out before from the from the geometry. Okay, so in particular, this provides evidence for the simpler argument that is when the operator exponential of alpha 2 is thought to be in the heavy regime, then you can think of it as some distribution picked on some heavy operator with this charge, maximal trace, with some spread. Okay? The spread now is what makes the difference between the intercorrelator when you have the maximal trace operator and the one from the geometry. But again, I want to point out that the one for the geometry is way simpler because that sum there decoupled the dependence on the essentially alpha and n. Now, as I said before, this is a divergent series, factorial divergence. So, which means in particular that if I want to think of it from the point of view of the geometry, the three-level contribution, each order in the tooth coupling is going to be a divergent series. So what do I do with it? So let me make first a picture to understand what's going on, and then I will tell you in words how the mathematics of this modular resurgence then solve the problem. So we need to, it's useful to think back again to the picture and think of it from the point of view of the flat space limit. And then in that case, I'm studying some correlation function, and then that I'm expanding as a limit from flat space, which means I'm looking to some bulk point. So this bulk point, of course, is dressed by all possible short string exchange, and this gives rise to the, say, genus G Virasoro-Shapiro amplitude. Now, different from perturbation theory, where you can do again similar game, at strong coupling this series is divergent, so one needs to fix it. Mathematically, the way to fix is that the series for the integral correlator I wrote before, you take it as a perturbative part. And then, since the observable is actually a good function, and this representation is bad, you need to complete it with some additional pieces, which are non-perturbative in the parameter you're expanding. Now, remember that we expanded in, for example, in the case, essentially we expanded in n, because the dependence on alpha is already captured. Okay? So n here is going to be my expansion parameter. And this non-perturbative is non-perturbative in actually 1 over square root of n. Okay? In particular, if you look at the genus G Virasoro amplitude, you're going to see that is asymptotically divergent series in this parameter 1 over square root of n. Yes. Now, since this is a good modular invariant function, it means that there should be a connection between these non-perturbative pieces and the perturbative one, and this is what goes under the name of this modular resurgence analysis. But the physical information about this non-perturbative part is going to come with some scales, some non-perturbative scales, some non-perturbative terms of the form e to the square root of n, and then there is going to be n tau plus m over tau 2, and some scale l. Okay? Now, in the case of the AVIV light-like operator, I have the opportunity to see that the scales L, they depend on alpha, and therefore I have the opportunity afterwards to see whether I can recognize this other scale L in the geometry. This matches with the intuition from the OP because somehow here in this description from the CFT of the genus G, the sort of Shapiro amplitude, I'm just taking into account short string exchange, but there are more. There are long string exchange. And this long string exchange have been discussed, well, the states have been discussed in the past by Magas and Hoffman, and they are the dual in the geometry to some Nambu-Godo worksheet that now spans the S5, not the ADS part that I discussed in the previous part. Okay? So you set up the problem for this in the geometry for the S5 part and this particular Nambu-Godo action, and then you find that you can actually rewrite this Nambu-Godo action in a very simple form. Yes, I understand. And this simple form is the following. So there are going to be some, it's a Nambu-Godo action, so there are going to be some derivative of the embedding coordinate with respect to the string sigma here. But now it turns out that after the dust is settled here, you recognize that the action of the Nambu-Godo string precisely takes this form. So it's complicated at the beginning, but then it simplifies. And this L plus, L minus are precisely the combination that you find from the resurgence analysis. And moreover, they satisfy a nice relation, which is totally obscure from the math point of view, but is L plus times L minus equal to 1. Okay? This relation also has some physical meaning, and has the physical meaning that if this is true, then the geometry is actually smooth. Okay? If you express this in terms of Q, then you go and check, and you see that's precisely the condition for the geometry to be smooth. So with this, it kind of gives a clear picture somehow in between the actual study of the correlator from M and the non-trivial information from the CFT of what's going on in a case in which I can study an area like correlator exactly. So a lot of information is going on. Of course, there are various generalization of this, but somehow there should be some catch, because as I said before, when I studied the maximal trace operator, I kind of ran into some complication, but then this complication in the end they kind of dissolve, and everything is nice for the state that corresponds to geometry. We hope that this works for many more bigger class of geometry, not just this is special to the stress energy tensor. And with this I will conclude, since I'm running out of time. Thanks for the time.
Some questions?
Yeah, maybe so does the computation that you can do with the wave equation and the geometry knows about this non-trivial fact?
No. No, that's the nice thing. So the geometry knows more than the correlator I input. So because, as I said before, to compute Eun, I do this computation with the phi in this phi. And you know nothing about the sphere part because you're in a consistent location. But to get those, you need to see also the sphere.